Morning,
Good
Professor.
morning.
Hey, Professor. I see you upload something on Blackboard, Pump 3, which is due today.
Say again?
I see you upload 03 pumps on Blackboard, like
Yeah,
a quiz.
that was the quiz from last Wednesday.
Okay.
But you should be able to see all of the quizzes now that we have taken.
Okay.
We'll go over that today. All right, so it is 11:31, so we're actually a minute late. So let us begin. Hope everybody is enjoying the snow, at least a little bit. Did anybody have canceled their teachers tell them that they're just not having classes?
Nope.
No? Guys, I am sorry that we have to have class. Truly am.
No such thing as snow days anymore.
Yeah, I mean, this year might be just different from other years. From the fact that, I mean, you guys know that you have to have a certain amount of weeks in the semester of how many classes you have to have, right? That's a state rule, and that's even for engineering with our ABAT accreditation that we have to do. So it's one of those things where I think it was my junior year, we had so many snowstorms that we actually had to get special permission from the state to have the classes actually count that semester, because we actually had like a 12-week semester, not even because there was that many snow days. And I think because we're already in that special circumstance, because we're at 13 and we have to have that extra week of learning somewhere fitted in, they're not even wanting to test that.
So Professor Callahan.
What's going on?
So earlier you were going on about ABET accredited, and I was wondering, do you know the reason why MarineOps engine is not ABET accredited?
Because it is not technically an engineering degree. It is not that's really what it is. It's not an engineering. You are studying to be a shipboard engineer, but that has nothing to do with ABAT. All right. So ABAT is all about, basically it's an accreditation program where it goes through and certify, Binghamton University has a mechanical engineering program that's met up to their standard. So it's a standard nationwide. All right. But MarineOps is not a engineering based. It's actually, I think it's an art. It's a Bachelor of Arts or something like that. It's the same thing as business. I don't remember correctly which one it is, but it falls underneath that accreditation. All right, which is the school basically saying this is what these kids have done for learning, and they've met the standards of the school. Whereas for engineering, it's you met the levels of the accreditation. All right. So technically it is not an engineering-based major.
Okay.
It's a bachelor's of science, I believe.
It's a Bachelor of Science?
Yes.
Yeah.
All right, thank you.
All
It is a
all
bachelor's.
MO degrees for decor engine. It's a bachelor of science.
Okay, sweet.
I think all of the degrees here are, except for like, what is it? Maritime studies, because that's a humanities. You just basically read history all the time.
All right. So that's basically what it is. All right. So at this point in time, you guys should be able to see the quizzes. I opened it up this morning. So this took a little bit longer than it usually would. Most of the time we will review the quizzes the day after we take them unless unforeseen circumstances. So like what we had in the first week of classes, some people missed and we had to catch them up because they missed the first week. So that being said, we actually have all the quizzes now. We're going to go through them really quick this morning. All right. And then we're going to go into today's lesson. So from here on out, whenever we do a quiz, the next class is what we're going to be going over it, unless, of course, somebody has missed it for something along the lines of STCW. All right. And then it won't open up until that person has taken it. All right. So the average for this one was a 71. All right. So that, you know, is the average. All right. Oh, and by the way, I don't curve anything. So just so you're thinking. Which of the valves listed below will cycle from fully open to fully closed when the valve handle is turned 90 degrees? The only valve here listed that does that is a butterfly valve. Everything else utilizes a valve handle and a valve wheel. All right. And a globe stop valve, I think I made that up. All right. So a lot of things you have to look out for is just because it sounds correct doesn't mean that it is. It's a lot of these things is that I will just make it up on the fly because I think it sounds interesting. Or if it's something along the lines of, which we will see in pumps, it may sound correct, but if we didn't go over it in class, then it's not correct in this class. All right. So remember what we've gone over. All right. A gate valve cannot be used to throttle due to what? And that's the eventual wear of the disc causing leak by. All right. Now, you cannot determine how accurately open a valve is open or closed. That's super incorrect. You can actually determine how open or closed it is at pretty much all levels. All right. So as soon as you're turning it and you go all the way until it stops on the lefty-loosey or the righty-tighty, the valve will be either fully open or fully closed. And then the distance between where the stem and the actual bonnet of the actual top of the valve will determine where the how much percent it is open. All right. The difference between a relief valve and a safety valve is a relief valve will open and reset at the same pressure, whereas a safety valve will open at a set pressure, but reset at a pressure below that. All right. So regulating valves can be controlled by what means, and that is everything. All right. Remember, if it can be measured, we can regulate it. All right. We can turn it into a signal, especially nowadays. All right. With digital controls, all right, with computers and everything else along those lines, we can even do that even more and more accurately. All right. So what valve can we use to throttle without other valves in line? The only one here that's listed that is a throttle valve is a butterfly valve. If it stated that you had two valves in line and only one of them is used for throttling, which valve would it be?
Gate valve.
Yep, correct. All right. So in the picture shown below, what is the pressure being regulated is the what force. All right. So we have flow coming from left to right from below. All right. And we can see that it comes up below this piece of gasket, below this piece of baffle material. All right. And that's going to counteract the spring force. And as it pushes up, it's going to close the valve. All right. In the picture shown below, the valve is maintaining what type of pressure, and that is going to be back pressure. All right. So it is not backflow. We did not go over any type of word like that. It's not downstream pressure. Downstream pressure would be over here in the relationship to the valve. All right. This is upstream, and it's not downstream flow. All right. So the only one that's going to be doing is the back pressure, the pressure keeping backwards. All right. Because it flows from left to right here. A bypass valve is used to direct flow around an isolated piece of equipment to allow continual operation. That answer is true. If we didn't have that, we would be shut down by a faulty meter. All right. A swing check valve allows flow in either direction when mounted vertically. That is false. All right. These can work in a vertical or horizontal. All right. What check valve, if mounted vertically, would allow flow in both directions? Who remembers that?
Could you repeat the question, please?
Yep. If a valve was mounted vertically, what check valve would you use?
A swing check valve?
You would use a swing check. Which one would allow flow in both directions if it was mounted vertically?
Lift check.
Yep, a lift check. All right, because it utilizes that plug, right, which relies on gravity to keep it downwards. All right, to flow back down and close off the valve. All right. So going from there, let's see, we're on question 10. A packing gland main purpose is to provide an area where packing material can be inserted to create a watertight seal around the stem. All right, so I drew this last class for everybody right here. All right, so what we have is in red, we have our actual gate, the gate portion of the valve, the disc. All right, in black is the bonnet. All right. Right here, where I have a number 1, the arrow pointing to, is our packing gland. All right, it utilizes a string-like material, all right, that you cut into pieces. Now, the green is the stem, all right, which I have drawn here on a vertical looking downwards. All right, if you were looking downwards that way, that's what this drawing is over here. So we have our stem in the middle. We do our packing material around in a circle. And we do about 3 layers deep, all right? So we would alternate where the cut is, all right, from one side to the other, where this glitter is because I ran out of different colors, all right? So each one is going to be rotated so that way it seals it up. Finally, we would have these black material right here, all right? And what that will do is it will push downwards onto the packing material, creating a nice tight seal, all right? Where'd it go? There it is. All right. So from there, any questions? We're going to go right into piping. All right. So this one, you guys did way better. Nice job on that. It was a 79, so pretty much an 80 average there. All right. When creating threads on a pipe, you need what type of tool? You all got it right. Good job, tap and die. All right. A union will create a watertight seal due to what? And that is a metal to metal contact. All right. The threads are what create the pressure, what create the force that actually create that seal. Okay. If you're confused on that, look to the piping pictures that are in the PowerPoint slides. All right. The actual photos that I posted to Blackboard. All right. To make a 90-degree turn with a piping, what type of fitting would you use? The only fitting that here would work is an elbow. For those who said T, how would you keep the flow coming out the third side? All right. Because in a bind, you could use a T, but what would you have to use?
Plug.
You'd have to use a plug. What else could you use?
Caps.
How would you use a cap onto another fitting? What would you have to add?
External threading.
Not external. Well, it would have to be external threading, but if they're the same size, how would you do that? If you have a T, right? And we have flow coming in this direction, right? We have a pipe coming in there. we have a pipe going out there to make a 90-degree turn, right? So we could put a plug here, which was already what was answered. But if we use the cap will be the same size as the fitting, right? So what would we have to do?
Would you have to use a tap and die?
Or
You
a
wouldn't use
coupling.
a tap, you
Just attach
Need
a
more pipe.
pipe.
you would need more pipe. All right, so if you added a little bit of a piece of pipe here, that would stop the flow, right? And we would get what we want here, which would be a 90-degree turn. So in a bind, you could either use and put a plug in to this spot and plug it, or you could add a small piece of pipe and a cap. All right. Again, this is just about being creative of what you have to do sometimes on a ship. You may be in an instance where you don't have an elbow, but it's leaking and you got to fix it.
How does a cap differ from the other piece that you were describing?
A plug.
Yeah, how does like a cap differ from a plug?
All right. So let me draw the T again. Here we go. So that's the T. All right. That's the flow of pipe. Shoot. Where's the pen? There we go. That was super weird. All right. So we have the pipe going out that way. All right. We have the pipe going out that way. All right. Now, we had the cap, and if we have a plug. So a plug is going to be what's going to go into it. All right. It's going to have a smaller diameter. All right. There we go. All right. And it's going to be either threaded like that, and it's going to be inserted into the fitting. All right. So it's made to go into pieces of material like that, and it will be popped out and it will look like that, and it'll be nice and threaded in there, and it will keep the flow from going outwards. All right, so that's the difference between a plug and a cap. A cap is going to go onto the external of our threads. All right, so the cap's going to be going around our piece of piping like that. All right, so this would be like a cut in half, whereas a plug is going to be going into the piece.
Could you use a nipple to connect the cap to the piping?
So you could use a nipple, all right, and that's what you would have to use. Or if you have if this is, it doesn't say what type of fitting this is, but if this is a copper fitting, you wouldn't be able to do that. Okay. So going from there, when you have to join two pieces of pipe together while one end is connected to the bulkhead and the other is attached to equipment, how do you connect them? That is done via a union. All right. If you use a coupling, one side is going to be de-threaded while the other is going to be threaded on. All right. That is going to be one of those spots where it's impossible to thread both sides on at the same time if they're both connected securely to equipment and or piping. All right. So piping with a diameter exceeding 14 inches is sized by the outside diameter. This is just a straight memorization, guys. That's really all there is to it. All right. True or false? Nipples can be used to combine two pipes that have internal threads. So if the two pipes have internal threads to them. All right, there's pipe number one with its internal threads. All right, again, it's connected via, this is going to be a cut in half look. All right, the nipple is going to be inside of it where it's going to have external threads that's going to go into the internal threads here. All right. So that is our nipple that is in red. All right. Now, from there, bolting up flanges, you should do it clockwise. That is false. All right. What is the actual pattern that we are looking to do?
It's like the star pattern, right? You go
Yep.
across and then,
So star pattern, pick a corner, pick a bolt, and go from there and go in a star. All right. When schedule increases, what happens to the pipe? 91% of you got this correct. Nice job. Your wall thickness increases. All right. It's all based on your wall thickness. Your outer diameter is not going to increase, and your inner diameter is going to decrease. All right. So you can get a thicker wall. All right. When sweating a copper pipe to a fitting, flux is used as what? All right. So flux is going to liquefy and boil off. It's going to create a vacuum inside, and that's going to suck that solder, that liquid solder, deep into the joint and make a full connection. And then finally, pipe thread is different from machine thread. All right, that is true. You cannot use machine thread, tap and die set for piping. All right. Now, finally, we have pumps. All right. Again, another good, nice little average there, 76. Good job, guys. So, first of all, a double acting reciprocating pump sends out how many volumes of liquid per cycle? You have to think about this. Is a cycle is the full up and down motion of a piston. All right. So you have both sides of the piston operating. That's going to be 2. All right. A Wilden pump is what type of pump? And that is positive displacement. All right. What is the technical name of a Wilden pump?
Diaphragm pump.
It's a what?
Diaphragm.
Yep, it's a diaphragm. All right. Wilden is the industry name. All right. To increase the pressure of a centrifugal pump, what can you do? The only thing you can do is increase the speed of a pump. All right. Now, this is technically correct if you need to go outside of the range of the pump, but for all purposes, you increase the speed of the pump. Okay. Yes, if you need crazy amount of pressure, if you want to go from 60 to 300 PSI, you definitely need to change out the pump. But if you're just going to increase it a little bit, you just increase your speed. All right. So if you have shut off head, all right, what does that look like on our chart? We have our, let's clear that and draw it a different color. We have our centrifugal pump chart, right? Looks like this. There is our, see, we have PSI, we have flow. We have our pump line goes like that. And finally, we have, do this. And we have a green dot right there. So, right at that point is a no flow scenario, right? We have shut off head. That's where that point is. We know that's shut off head because we can follow our blue line, which is a closed valve, all right, which is allowing no flow through. All right, so that is shut off head right there. All right. So a relief valve on a positive displacement pump will be located where in the system? All right, and that's from the discharge side. All right, it's sensing from the discharge side and going to the suction side of the pump. It is not going to be coming from the suction side. We are not going to be relieving the suction side. All right, so we're going from the discharge to the suction. All right, going from here, which of the 4 pumps in illustration GS0179 show the correct way of our lobe pumps? All right, and that is letter B. This is a direct copy paste from the Coast Guard book. All right, same question. I've actually had this question on my thirds exam. Okay, so on the pump shown below, what is letter B representing? All right, if we look at letter B, we can see through this entire piece, this is a centrifugal pump. It's just a side view of an actual centrifugal pump. And it's pointing at this entire face here, all right? This piece right here, all right? That is the impeller, all right, which 94% of you got correct. Now, letter A is representing this entire area, all right? Both the center, all right, which is our suction or our eye. So 88% of you got that correct, all right? What is C and D representing? So what is C representing?
The casing.
Yes. What about D? Got a chat response. It is not the
Powered
discharge.
shaft.
It is going to be the shaft. All right. So what is E then?
E would be the discharge.
E is the discharge. All right. So D is our shaft, C is our casing, A is our suction, B is our impeller, and E is our discharge. All right.
In that case, isn't the casing called the volute?
So yeah, we have our, let's go into annotate, we'll go red. All right, so remember, we have our impeller right here, right? That's what's drawn in red here. All right, and then I'm gonna go green for our casing. So we have a volute is going to be that whole area where it actually discharges. All right, so this is our volute right here, like this area. All right, so the outside portion is the casing, but the volute is what actually makes up that area where it gains that kinetic energy and goes upwards. Okay, so if C was pointing on the direct opposite side, like if it was pointing like all the way over here, like think 3D, all right, on the opposite side of that suction, then yes, that would be the volute / casing area. Okay. Good catch. So gear, lobe, and screw are all what type of pump? That is a positive displacement. All right, kinetic and centrifugal, those are, centrifugal is a part of the kinetic area and kinetic is not part of a positive displacement. All right, and reciprocating is a piston-driven pump. All right. True or false, positive displacement pumps will send a fixed volume with each stroke or rotation. That is true. Positive displacement does not care. It's always going to do a fixed volume. All right. Any questions on that before we continue on? All right. So, as you can see, we are not in class today. Everybody knows that. Everyone got the email. All right. So for lab, we did not have lab today because we did not have, and we're not holding in-person classes. All right. So with that, tomorrow, it's going to be decided sometime later today whether we're going to have in-person classes tomorrow. If we are remote, there is no 540 lab tomorrow. All right. If we are in person, then we are just, that's going to be the email. That's just like an email getting from me. All right. So if we have an email that says we are resuming in-person classes Tuesday, that means we are going to 540 lab tomorrow. Okay. So look for the communications email. Now, which way it goes to, if we have lab tomorrow, if we don't, it's going to determine how I'm going to deal with people with making up these labs. All right. So next Monday, for people who missed this Monday, you're going to basically continue like you didn't miss today. All right. So you're going to follow everybody else's schedule. So we're going to have to find the time to make up this lab. All right. One way, shape, or form. That's my portion to worry about. You guys will have an email that'll come out to you. Like I said, one way, shape, or form, it's going to happen. And it all determines what's going to happen tomorrow. All right. And how I'm going to handle this. Whether I'm going to have 40 kids or 80 kids that are going to need makeup. All right. So that's where the determination comes from. Everybody get it? So just kind of look out for an email from me. It's going to happen today or early tomorrow morning. We'll see. All right.
Any questions on that? Any questions on the quizzes? All right. So let us get going.
Professor, I had a question.
Yep. What's up?
For the quizzes, are we able to go back and see the questions that we got wrong? And
Yeah, you definitely should be
Yeah.
able to do that now. I allowed it since this morning. I'm
Okay.
putting that up. If you guys can't, let me know, because that means I did something wrong on Blackboard. Okay. For those of you who took the quizzes on paper, I have yet to grade them. So I will grade them probably this afternoon, post the grades, and I'll probably do it in the feedback so that way you guys can see what you got wrong. All right. Any other questions? Okay. Let me get the PowerPoint going. Oh, shoot. That's not what I wanted. All right. Let us begin. So, steam reciprocating pumps. All right. If we look to this, where do we have a steam reciprocating pump in our engine room? What is it called? I mentioned this last week. The other class failed me. Don't you guys fail me as well? Choose a different pen color. What do we got in the chat? Where did the chat end up? That's the other question. There we go. It is not a simplex. All right. We utilize a duplex.
Can you repeat the question?
Yep. Where do we utilize a steam reciprocating pump in our engine room? What is it called? It's lower engine room, starboard side. It is a duplex.
Is it the generator?
It's not the generator. No, that's a turbine driven.
The
Is
circ
it
pump?
the-
It's the what?
Circ pump?
It's not the circ pump. That's actually a mixed flow centrifugal.
Is it the reefer system?
It's not in the reefer system. Nope.
Can you repeat the question one more time?
So where in our ship do we use a steam reciprocating pump?
In the lower engine room,
Yep, starboard side. What's it called?
import feed pump.
Mm-hmm. That's it. All right. So it's the in-port feed pump. All right. INPORT feed pump. All right. So back in the day when this was a bulk carrier, we only had the ability for steam, right? We didn't have actual diesel generators on the ship. So when we were in port, we were in port for a while. Relative terms nowadays, it would be a week to unload or to load. All right. So it would take a while. But when you start up a steam plant, it takes a while to do so. So by the time we'd shut it down, we would need to starting it up to warm everything up. All right. So we still need electricity. All right. And the only thing we would have is our TGs, our turbo generators. So we would only need to keep one of those going, and we wouldn't need to send all this extra steam to our propellers, all right, to our main propulsion plant. So that's why we use a in-port feed pump. All right. So in this in-port feed pump, we have suction, we have our discharge, so that's our liquid for our feed pump side. All right, this is our feed water. Now we have our exhaust and our supply of our steam. All right, utilizing this slide valve, we could see, can I pause this? Nope, doesn't look like I pause it. All right, so if you look at it, how it slides, all right, one way it's only allowing steam in one direction, and the other, it'll allow steam to flow outwards, going this way, all right, or it flows out this way. All right, you can see how the steam valve, all right, steam comes up across over here, and it will fill this side in. So all of the exhaust here is going to come up and through that exhaust line and come out that direction, and vice versa. Okay, so if it goes this way, we have steam supply going to go in there, and all of the exhaust here is going to come up and go out our exhaust that way. All right, all due to based on that slide valve right here. All right, and it goes back and forth, and it pumps some water. All right, just a positive displacement, steam-based feed pump. All right, so this is our turbine feed pumps. All right, this is our main feed pumps. All right, also starboard side of the engine room. Who knows where? Who can remember? So I just drew the shaft. All right, that's the ladder well going down. All right, so that goes out to the shaft. That's aft. We have a door right here that goes into lower engine room, right? So this is forward. All right, we have our auxiliary condensers right here and right here. We have our reefer system over here. Testing your knowledge on your ship training that you guys did. I know you didn't do lower engine room yet. So that's our reefer system. All right, we have our import feed pump. All right, and right here, this box and this box. Those are our feed pumps. Those are our main feed pumps. All right. So we have our big condenser over here. All right, so you come down the stairs, you're on the starboard side. You're walking past these two feed pumps as you go down to Shaft Alley that way. All right, so that's what we're talking. That's the equipment we're talking about is our two main feed pumps. All right, we'll see a picture of it in a second. So quick drawing that we have here, we have our exhaust from our turbine. That's an exhaust for steam. All right, we have our supply for steam. We have our suction. This is coming from our DC heater. And now it discharges. Ooh, I'm gonna change paint colors. That does not help anybody. Let's go red. Now, we will talk in depth about this when we hit steam, but know this for now. We have two discharges. We have main and auxiliary. All right. Now, both go to the boiler. All right, they both lead directly to the boiler. Well, does anybody see any major difference here between the two? They're both leaving the same discharge side of the pump, right? They're just getting split off from each other. So is there any difference? This is our main and auxiliary feed water.
You can have one closed for maintenance.
You have one closed for maintenance. All right. So that's the only thing that we can really see, right? They're the exact same fluid, correct? So this is the big difference between the two. The main one has a regulating valve on it. So it's automation. The auxiliary side is there for backup. All right. And in certain situations, you may have to run a little bit of auxiliary feed going into the boiler. All right. That's some higher level stuff that we don't have to talk about, but it basically can add a little bit of extra feed water in situations that you know as the engineer it may need. Okay. So one is automated and one is going to be manual. So the auxiliary is manual. All right. But just know they both go to the boiler and they're both the same feed water. They're not different. All right. They both come from the same pump. All right. It's kind of like having twins, and obviously you have a favorite. All right. So going from there, that is our main feed pump. Does everybody starting to see and recognize this giant piece of equipment in that lower engine room? All right, everybody remember this for the most part? All right, so there's our exhaust, there's our supply steam, here's our suction coming in. All right. There's our suction again. This is looking like you're coming from forward, you're looking aft. All right. You have your main feed line and you have your auxiliary feed line. All right. Now, here is a new word right here, trip. OS trip. All right. Does anybody have an idea of what OS trip means? Or just what OS means? Does purple look better? I don't think so. There we go. What does the word O/S would mean? All right. So over speed. All right. So it's an over speed. All right, that's what everybody will call it, as an OS. If you have to write it, a lot of people will just say overspeed trip. All right, O/S means the same thing as overspeed. Now, the word trip, does anybody have any idea what this may mean? Just the word trip.
It gets set off for a certain condition, like, I don't know, maybe like pressure, temperature.
All right, so both you and Pulley are right together. So Pulley said in the chat that it's going to be operational shutoff, like in cutoff, and you were saying it's going to be at a set pressure. All right, something. So basically what's happening here is trip is like a hard reset. All right, so you can have an overspeed trip. You can have a different types of trips, and I don't want to say anything more because it will confuse you guys, but you can have different trips for systems that will basically be a hard reset. All right, so if your computer blue screens, right, the mouse stops responding, what do you guys do?
Use the keyboard.
You would do like a Control-Alt-Delete, but what if that doesn't happen? What if that, like, it is seriously hard lockup?
Yeah, it's reset button time.
It's reset button time, right? So you're doing a hard reset, right? You're cutting power and you're going to re-add power back into this. All right. So the difference here is a trip doesn't re-add the power back in. Once it trips, it's like pulling the plug. All right. So that's what we're doing. We are pulling the plug on whatever's happening here, but it's only pulling the plug when it overspeeds. So if it starts to go too fast, all right, remember, this is a turbine. So if this thing starts to like really ramp up, and we don't want this thing to ramp up that fast, this thing is going to kill the power. All right, it's not electricity, it's our steam supply. All right, so that's what the word trip is. We are going to be tripping it offline. All right, so this is an overspeed trip. Make sense? Good. So we're going back into the system, all right? So we have to look on how this controls, all right? Here we go. We're talking about regulating valves again, All right. So here we are. We have something called a pilot valve. This brown fluid right here is coming out of a lube oil supply. So that's coming out of a lube oil pump. So I'm going to draw it in right there. All right. So we have our lube oil return. That's going back into a sump. So basically a tank of lube oil, low pressure. All right. And we have an operating cylinder with a pressure regulating valve for our steam supply. All right. So that's steam supply. Okay. Now, we have our feed water, our feed pump pressure, discharge pressure. All right. This is what we are monitoring. This is our input. All right. We are going to be inputting feed pump discharge pressure. But what we are going to be regulating is the steam supply going in, which in turn is going to change the feed pump pressure. Okay. Now, if our pressure increases, all right, the feed pump pressure increases, what happens? Just like a regulating valve, what's happening in that spot? What happens in here? That is a terrible color.
There's an increase in flow.
It's going to be an increase in flow, but what's going to be happening? Remember, just think like a regulating valve. All right, we have our spring in brown here. What's going to be happening there?
Spring's going to be pushed upwards.
Spring's going to be pushed up. So if we can overcome that spring force, which is what happens, all right, so we push upwards. Notice our pilot valve between those two positions. Here we are here. And as it increases, we move that pilot valve upwards. All right, notice this. This area right here, this operating cylinder. All right, it's going to flow from high to low pressure. So it's flowing this way, flowing this way, flowing this way. It goes into the pilot valve here. It can't go in that direction, right? So it only can flow here and go down into low pressure. It goes to our lube oil sump. All right. Well, this is a piston right here. So that's going to go downwards. And if that's directly connected to a valve, what happens to the valve?
Shuts.
It's going to shut. All right. So it's going to start closing the valve. So what happens to our steam supply?
It's restricted.
Restricted. So we're not going to have as much, right? So that's how we regulate our steam supply with feed pump discharge pressure. Pretty cool, right?
Wait, so if it closes, the pressure goes up, right? So the valve itself. So if the valve closes, doesn't the pressure also go up?
So you're thinking like it's a steam pressure, like we're regulating this. So think about it. We are monitoring our input is our pump discharge. Okay. But what we are going to actually be physically moving is the steam pressure going in. So if our steam pressure valve is at 50% open, and we go from 50% open, all right, there is the gate right there, to 25% open. All right, it's a lot farther closed. If we don't have as much steam going into a turbine, our turbine's going to slow down. All right, so if it's going to slow down, we lose pressure. All right, because it's a centrifugal pump, so we go down on that chart. All right. Now, as it goes down on its chart, we're going to decrease our feed pump pressure. All right, because we are trying to look for a specific pressure of our pump. More importantly, the discharge of our feed water. Okay.
Oh yeah, okay, I see. That's not, yeah.
So if we do the reverse, all right, say it overcorrected. All right, the feed pump pressure decreases. All right, look what happens. The spring pressure overcomes the discharge pressure. The pilot valve, now we have our lube oil pump adding fluid into here. All right, it doesn't go into the lube oil return because that's blocked off. So it adds into our operating cylinder and it pushes up on that piston, right? And that's going to open up our valve. And then we're going to get more steam flow, which is going to increase our RPM of our actual pump, which will increase our pump pressure, right? So that's how this thing is operating. It's quite simple on its operational. All right. The last thing that it can do is right here. This is our overspeed. So if the overspeed trips, look what happens. This operating cylinder is going to flow fluid directly down into our lube oil return. It doesn't matter how much this lube oil supply is going to be pumping in. All right. It will be dumping. It would be like opening up your bathtub and having the water going into it at the same time. It does not matter. It's going to dump. All right. And if that dumps, there's going to be no fluid pushing up on that cylinder, right? So it's going to close that valve, which will shut off our steam, which will in turn turn off our pump. Okay. Last thing, which I have not mentioned here, but it's if you saw it in the top left-hand corner, something called a reach rod. All right. So the reach rod up here has a hand wheel on it. All right. Basically, it's a threaded piece of like valve kind of thing, and it has just a normal hand wheel like you would any other valve. All right. So in this instance, we are going to be loosening it. We're going to be lefty-loosey here. All right. So if we loosen this valve, I'm drawing it this way because the other class got confused on what was happening with this arrow. All right. So if we loosen it, what happens to the spring tension?
Lower spring tension.
You're going to have a lower spring tension. You're going to have a lower amount of force. Okay. So if you have a pen, take out the spring inside of it, and you push down on the spring halfway its distance, right? It's giving a certain amount of force back to you, right? But if you lessen up about 25%, it's less force, correct? That is pushing back into your fingers. All right. The same thing is happening here. So if we loosen or we relax the spring, will the pump discharge pressure, will it be easier for the pump discharge pressure to overcome the spring pressure or harder if we loosen the spring or relax the spring? What will happen? Is it easier or harder for the pump pressure to overcome that spring pump?
It's easier.
It's easier. All right. So it's easier for the pump to overcome that spring pressure. All right. So if we loosen that spring, the same thing as if the pump discharge pressure was high. All right. So that's how, if we loosen that spring, we can decrease our steam flow and we can set a lower operating point of our pump. All right. But if we increase, if we take our pump and we take our spring and we increase the pressure on that spring, it will be harder for the pump to overcome that spring pressure, right? So the exact same thing will happen. We can have a higher set point, which will increase our steam pressure going to it because it will be harder for the pump to discharge pressure to overcome that spring force and push it upwards. So it will need more pressure. So open up the valve for our steam, increase the steam turbine's speed, which increases the pump speed, and it's going to push and allow it to actually overcome that spring pressure eventually. Okay? Does this make sense? Does anybody want me to go over any portion of this again? Because it's the first time you guys are really seeing a system of this nature.
Sir, could you go over back the overspeed?
Okay. So the overspeed trip, when it could be you could push it, or whatever it's sensing, when it overspeeds, all right, you're removing a blockage from right here. It would be like removing the plunger from your bathtub, all right, with your bathtub filled. And all this lube oil in here will dump straight into your lube oil return, no matter what is happening in this pilot valve over here, all right? And when this dumps, there's nothing keeping up this piston that I'm circling in right now, and it's going to lower and it's going to close the valve for the steam, and it will shut off the pump because it won't have an external force spinning the turbines.
Excuse me?
Yep.
Is this for the safety of the whole machine system? So like it doesn't, okay.
So it's the safety of this, of the actual turbine, the pump, and also you.
Okay.
An overspeeding turbine is really, really bad. All right. So, any more questions? All right. So let's look at a generic fuel oil transfer, but let's look at what we have in front of us. So taking a look at what we have here. All right. Hold on, let me. There we go. That was super weird. So look what we have here. This is called a tracing or a line diagram or a plate. This is what you guys are going to be producing, but for the steam water cycle. All right. So a quick rundown on how to read these. All right. You can see our valves. All right. And one thing that we can see right here, there's like a little blip. All right. And I'll show it on a larger scale, which is right like this. All right. So what that little piece right there is showing with this little bump, all right, that means that these two pieces of pipe do not connect. All right. That's what that bump means. All right. But right here, you can see that there's a T, right? That T shows that these pieces of pipe, those three pieces, are actually physically connected. Okay. Now, the next thing, from here to here, there's a distance of pipe, right? That's a physical distance that we can see. That may be a foot, maybe 6 inches, and maybe 25 feet. Is this drawn to scale, that piping? So this is not drawn to scale. Okay. We don't care about the length of pipe here. All right. What we care about is order of components and how they connect. So even things like this elbow right here may not even be an elbow. All right. That may be a straight long piece of pipe. All right. So what it's showing is that everything is connected. All right. So we don't care about fittings. All we care about is valves, components, strainers, pumps. All right. Order of the system. The lines are just there to show flow and how they connect.
Excuse me?
Yep.
When does wall diameter come into play?
Wall diameter
pipes.
Pipes. So that won't be shown on this type of diagram.
Okay, this is just like running it where it's coming from. Okay.
Yep. Where basically all it cares about is components. It literally does not care about the piping itself. It's the piping is just shown as a line to go from component to component. All right. So like I said, this can be a mile of piping right here. And between this and this, even though it's a longer piece of pipe, a longer line, this may be 3 inches in the real life. Or it may be, 3 miles if we're working shoreside. All right. But it's still represented in the same distance as what 3 inches may be. It really, truly doesn't matter how long these pieces of pipe are on your drawing. We'll get way more into this when we actually start discussing tracings, but this is just the basics of how you would read these. All right. So let's talk about a fuel transfer manifold. So a fuel transfer manifold has these 3 sections of plates, all right, that create 2 voids. All right. Now we have a bottom section that we have horizontal plates. All right. And that allow us to have how many different tanks we would be able to suck and fill from. All right. So this would be tank 1 section, tank 2, tank 3, and tank 4. All right. Now, each one of those horizontal sections have a pair of valves that go into it on top. All right. Those are the those are the valves that will lead to these pipings that will actually go off to tank 1, 2, 3, and 4. All right. Lastly, what we have is a suction pipe and a fill valve, a fill pipe. So what happens is if we want to take suction from tank number 2, all right, so we're pulling in a flow, it fills this whole lower cavity, all right, this whole lower area, and it will come up. Keep in mind there's a plate that's separating these 2 sides, and it will come up and it'll fill this whole left side here and go out through the suction. All right. Now, if we want to fill tank number 4, we're going right back around in there. We have a pump like that wants to just flip back around. So everything that comes out of 2 is going to fill that lower section. It's going to fill that whole entire left-hand side over here, and it's going to go out that suction pipe, go through a pump, come back into the fill. It's not going to go into 1 because 1's valve is closed. It's not going to go into 2 because there's a wall right here that separates the 2 sides. It's not going to go into 3 again because that valve is closed, and it's going to go only into 4 because that valve is open. All right, so that's how a fuel oil transfer manifold works. All right, does this make sense to everybody?
Yes.
Okay. So this is a generic fuel transfer map, something that you might run into. So if we want to take suction from this tank right here, I'll call it tank 1. All right, you can see how we followed that line. All right, so we went through this valve right here, we went down, went across, we went through this valve here, through a strainer, and then into our pump. All right. Now, if we want to fill tank 2, all right, we have our pump. It comes out, goes down around this valve, all right, because there was a little hump there, and it goes out to tank 2. All right. Now, here's another example that we could run into. All right, so we're taking fuel on board. All right, so we're taking it onto the ship. It's coming from our deck connection up on deck. All right, so it comes down and it gets added into the line at this point. All right, it's pretty easy. We open up that valve and we go to the manifold, right? We go into the fill side of our manifold. And we want to fill those 3 tanks. All right, and same thing if we wanted to do on the other side. We would just open up this valve over here and pop open those 3 valves, right? That's pretty easy. But if we want to fill it at a faster rate, there's another thing that we can do with this setup that we have here. All right, we can actually flow it through the fill side. All right, so that is technically our fill side of our manifold, correct? Our suction side. All right, and that's how we can get a faster paced filling. All right, this is manipulation. We are using our environment. We are using our piping around us to control our flow, to control the pace at which this thing works. All right. So every single piping map is going to be different, but it's up to you as the engineer to know what's the fastest and easiest way to operate these things. All right. Next up, we have a bilge, ballast, and fire manifold. All right. We have a new word here, sea chest. Does anybody know what that means?
Is that where any like
Got two people.
it's just where like all the like gunk that you get up pretty much, like sand, rocks, shells, whatever. You just put it all in the sea chest.
Nope.
You reroute it there.
That's not the spot where we do all of that. Who else has an answer?
Was the sea chest where you put seawater for firefighting purposes?
All right. So this is not the area where you put anything. Okay. So this isn't like a storage tank. What it is a literal box that comes out from the deck. All right. So this is you, the engineer, standing on deck. All right. It could be down at tank top. It could be in the bilge. And what it is an area where you have seawater below. All right, so it's all below on the bottom of the ship. It fills that cavity in there. All right, and this is where you would actually pull seawater into the ship. So it would go through its strainers, right? And then it would go out to a valve and then off to whatever system you have in place for it. All right, so it's the area of the ship. This is the sea chest down here. That is the area where you can actually access and pull in salt water, whether to your coolant systems or to your to make freshwater generation and all of that kind of stuff. All right. And for the person who said with sand and everything like that, that may be collected. If you are really close to bottom, yes, you could collect sand and stuff, and then you can have some serious problems with your strainers. So you could have something like that. Now, that's your sea chest. All right. If we look at our bilge manifold and our ballast, notice we have two different circles there. We have a half moon and a full moon. All right. So looking at it, this is our bilge manifold. So if we open a bilge manifold, it utilizes the valve that acts like a check valve. All right. So you can open it, but until you have a low pressure above it, all right, created by a positive displacement pump, would you actually be able to create a suction and open up said valve? All right, so this would not work in a centrifugal pump application. You would need this in a positive displacement pump to pull from a bilge well. All right, but with a ballast manifold, you want full control where this is going to go. You may be going from one ballast tank to another. All right. So you would want to have the ability to suck and put that water somewhere else. It may go to another ballast manifold, all right, where you'd be reballasting. All right. So going from there, you can see that there's just the rest of this PowerPoint slide is basically different examples of how you would be operating this system based on a line diagram, how you would go from one place to another. All right. So that's our bilge. This would be our ballast. So if we wanted to send ballast overboard, because it's just salt water, and those are just saltwater tanks, we legally can put ballast overboard, all right, with no repercussions. Or in this example, we can also send it to another ballast manifold and send it from one ballast tank to another. All right. And then finally, we have our fire main. So how to charge our fire main system. All right. And how we can go forward and aft peaks and discharge that overboard as well. All right. So any questions there?
Are we gonna get some practice with this, or should we just study what we went over today? Like, I know we should study anyway, but are we gonna get any more practice?
What do you mean? practice?
Like visuals or like scenarios where we have to find out the best piping. I don't know, anything like that.
So I would just really look at certain pieces of piping. All right. Look at that fuel manifold and challenge yourselves, like as far as studying. If I would challenge myself to go from one tank to another, how would you do it? All right. Just don't follow exactly what's there, but looking at your flow arrows that you have on the piping, can you go one direction or another? All right. And see if you can. Don't just follow what is exactly there. You can always create your own practice scenarios. All right. Now, at this point, you guys have learned everything for your examination, which is going to be on the 10th, so a week from Wednesday. All right. We have also finished pump operations, so that means class on Wednesday. We are going to have our pump operations quiz. Again, make sure you bring your laptop. I will be bringing extra quizzes for those of you who can't connect to the internet or anything else like that, or don't have a computer with them. Okay, so make sure you bring your laptops to class on Wednesday for a quiz. The 10th is going to be paper. All right, so you don't have to worry about that. Everyone's going to be paper-based. But from this point on, you guys are going to need to be studying for this test. Wednesday, we have the quiz, and we go right into freshwater generation right afterwards, which is not going to be on the first test. Monday, since we worked at a fast enough pace, it opens up the day for if anybody has any questions. All right, dedicating to half the class to questions. All right, if no one comes with questions, I'm just going to go right into freshwater generation part 2. All right, so this is your time for anything you guys have. Questions do not mean, can you go over everything of valves? That is not a question. Okay, so study over the weekend, study this week, come with things that you guys are confused about. All right, and it's your time. I'm not going to be just going over and reviewing. All right, so it's your time to use it. If you don't, we're just going to go into freshwater generation. All right. So that's the plan for the next week and a half. All right. So quiz on Wednesday, test next Wednesday, question reviews on Monday. All right. If there is no question review, then we're just doing freshwater generation. All right. Other than that, does anybody have any questions? All right.